So we've been talking about limiting reactants, theoretical yield. The examples we did were all in moles, but in real-life applications, we use grams. The reason that we care so much about what's the limiting reactant is that, just like cooking, if you set out to make pancakes, you're probably not going to have just the right amounts of ingredients for everything in your kitchen. You're probably going to have extra of something. Like with the pancakes, you probably run out of eggs first, but you got plenty of baking soda, plenty of flour, right? And that's the way it is in a chemical reaction. You rarely have exactly the right amount of each reactant. In an industrial application where you're trying to make something to sell as a product, you want to make the most use of whatever the most expensive ingredient is, and then have extra of the cheaper ingredients left over. Or sometimes, you get a product and it's not just the product you're looking at, it's got some other stuff in it too, and so then you're going to choose your limiting reactant so that you don't have something in your product that's hard to get rid of. So in doing these calculations, we're going to have a gram to mole conversion at the beginning and a gram to mole conversion at the end, just like we were doing before when we were just calculating amounts. So really, we're not doing anything different. Here we have a problem. If we have 53.2 grams of sodium and 65.8 grams of chlorine, what are the limiting reactant and theoretical yield? So what we'll do is we'll read the question, and then we'll make a note under the chemical equation of the amounts. So it tells me I have 53.2 grams of sodium. So I'll write that under sodium. 65.8 grams of chlorine. 65.8 grams of chlorine. The fact that I'm given two amounts there of different substances, the two different reactants, tells me this is going to be a limiting reactant problem. Two amounts given, that means I'm going to do two calculations. The question, what are the limiting reactant, we'll save that one for later, and theoretical yield? Well, theoretical yield of what? In this equation, there's only one product. So when we're finding a yield, we're always finding amount of product. Sometimes there's more than one, and it should tell you which one we're looking at. This one doesn't mention the theoretical yield of what, because there's only one product. So we're trying to find how much of this can be made. So how many grams of that can be made? It does not specify grams. It should. So the idea here, just like with the pancakes, is we take the mass of sodium, we figure out how much product we can make. We take the mass of chlorine, we figure out how much product we can make. And whichever gives us the smaller number is how much we can make. So the overall pattern here is grams to moles to grams. So we'll just start out with 53.2 grams of sodium. I need to convert that to moles of sodium. We'll always have moles in the middle. And from that, I'm going to go to, I'm not interested in how much chlorine, I'm interested in how much product can be made. So I'm going to go to moles of product, sodium chloride. And because moles is not something that we can directly measure, we need to get to grams at the end there. Okay? Now we just fill in the units so they cancel out. Once you get all the units in place and make sure that they're canceling correctly, then you can put the numbers in. In the middle, we have the mole ratio, and we get those numbers from the balanced chemical equation. 2 atoms of sodium will yield 2 formula units of sodium chloride. So this ratio is 2 to 2. You can write 1 to 1 if you want to. It doesn't really matter. The first term is a molar mass. Here it's sodium, so we don't have to calculate. We just look on the periodic table. 22.99 grams is the mass of 1 mole of sodium. For sodium chloride, we're going to have to do a very brief calculation. We got 22.99 plus 35.45. So 58.44 grams is the mass of 1 mole of sodium chloride. So then you do the calculation, 53.2 divided by 22.99 times 2 divided by 2, those cancel out, times 58.44. My answer should have 3 sig figs, 135, add 2 more there, 0.23 grams of sodium chloride. That is how much sodium chloride I can make if I have enough chlorine, but we don't know yet. So then we do another calculation. It's very similar. 65.8 grams of Cl2. I'm going to convert that to moles of Cl2. And then going again to moles of product. And then grams of product. Grams to moles to moles to grams. Yes?
The moles of product, that's, we always look at the product to put up the moles there. Like in the mole ratio, you said.
In the mole ratio?
You said it like the moles of product, so it's always going to be the moles of product.
Well, in this one, we're calculating a yield, and so we're going to moles of product. If you were doing a different calculation where they were asking, say, what mass of chlorine would you need to react with this mass of sodium, then you'd go grams of sodium to moles of chlorine to grams of chlorine. So we're going to put the units in so they cancel out. This is not the only way you can do these problems. But from years of teaching Chem 3A students, this seems to be the most straightforward, easiest to remember way. And sometimes it's better to just take the slightly longer way rather than getting lost in a shortcut. So we got all that set up. The last term ends up being exactly the same, so that saves us a little time. The mole ratio, 2 moles of sodium chloride, but this time only 1 mole of chlorine. 2 moles of sodium chloride to 1 mole of chlorine. And then here, the molar mass of chlorine will be 2 times the mass of chlorine. 70.90. The balanced chemical equation is giving you the correct formulas. We are looking at Cl2. So we need to calculate the mass of 1 mole of Cl2 molecules. It's not just Cl. So we do this mass, 65.8 divided by 70.9 times 2 times 58.44. This is also going to have 3 significant figures, 108.47 grams of sodium chloride. We choose the smaller number, 135, 108. This is smaller. This means that once I've made 108.47 blah, blah, blah grams of product, I run out of the reactant, and so I can't make any more. So this is the theoretical yield. So it's asking for the theoretical yield. It's this number. It would round to 108, right? 3 sig figs. and then it's asking for the limiting reactant. The limiting reactant is the reactant that gave us the smaller amount of product. So if you look at your your theoretical yield and see which reactant gave you that. So chlorine is our limiting reactant. Any questions? Yes.
You know, for 58.44, would you aggregate that just NaCl?
Yeah, just adding the 22.99 with 35.45.
It don't need to be like CO2? I have to add it twice.
No, because in the formula for sodium chloride, there's one sodium and one chlorine.
Okay.
So chlorine being diatomic is only when it's by itself. Because over here, the chlorine is fine because she's out on a date with sodium. So she's fine. She just doesn't like going out by herself. And so here she took a friend with her, girlfriend. Let's do another one. Ammonia can be synthesized by this reaction. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? So again, I've got my balanced chemical equation. I'm going to use it to organize the numbers. 25.2 grams of nitrogen and 8.42 grams of hydrogen. The question is, what maximum amount of ammonia in grams? Well, so there's ammonia. That's our question. How much of this? And the unit we want is grams. This question doesn't say anything about theoretical yield. It doesn't mention limiting reactant, although it's in the title of the exercise, but it doesn't mention limiting reactant. So how do we know that it's a limiting reactant problem? Because we're given masses for both reactants. That's the clue. If you've got masses for two reactants, you're going to do two calculations. If there were three and they gave you all three, then you'd do three calculations. I like to do the first one first. So I'm going to start with the hydrogen. Grams to moles to moles to grams. So this many grams of hydrogen. It is H2 because here hydrogen is by itself and it is a diatomic element. So I'm going to go to moles of H2. And then I'm going to go to moles of where the question mark is. Moles of NH3. And then I'm going to go to grams of NH3. It's the same pattern every time. You learn the pattern, and then it becomes easier. You're like, oh, well, I know how to do this. I just do this, this, and this. The numbers are different. The letters are different, but the pattern's the same. So after we put the numerator units in, we put the units in the denominator. Down here we've got moles of NH3. We get all the units first, and then we look for numbers. Moles in the middle. This is the mole ratio. There's a 2 in front of NH3, so I'm going to put 2 in front of NH3. And there's a 3 in front of H2, so I'm going to put a 3 in front of moles H2. 3 moles of H2 will make 2 moles of NH3. That's where that comes from. The mole ratio here is the only place you use those coefficients. Don't stick them anywhere else. Don't stick them over here or down there, just in the middle. The first is the molar mass of our reactant hydrogen. So 1 mole of H2 is 2.016 grams. That's just the molar mass from the periodic table times 2 because it's H2. For ammonia, you can do the math. 1 mole is 17.034, if I remember correctly. So it's 3 times 1.008 plus 14.01. Yeah, 17.034. So 8.42 divided by 2.016 times 2 divided by 3 times 17.034 equals. This would also have three significant figures, as commonly happens in problems like this. That's grams of ammonia. What do we need to do next? The second equation. So we figured out if we use up all the hydrogen, we can make this much. Now we have to see, well, what if we use up all the nitrogen? You can't tell by looking at them, well, this is much smaller, that must be limiting. Not necessarily. You gotta just do the calculation. So 25.2 grams of nitrogen. Grams to moles to moles to grams. So I'm going to go to moles of nitrogen to moles of the same thing as I did in the first one. Moles of ammonia, because that's what I'm trying to find, to grams of ammonia. And then I put the units in so they cancel out. So moles of ammonia cancel, and moles of nitrogen cancel, and grams of nitrogen. The last term is the molar mass of our product, and so it's the same, so we don't have to calculate that again. The mole ratio comes from the coefficients here. 1 and 2 will make 2 NH3. And then we need the molar mass of nitrogen. 1 mole of nitrogen is 2 times 14.01, which is 28.02. Any questions? So then we just do the math. 25.2 divided by 28.02 times 2 times 17.034. And this equals 30.639 grams of NH3. So how much ammonia can we make? 30.6 grams. Because that's the smallest amount. When we've made this 30.6 grams, we've used up all the nitrogen. It's hard to see it when it's crossed off like that. We've used up all the nitrogen. There is leftover hydrogen, but we can't make any more ammonia because you can't make ammonia without nitrogen. Any questions? Let's do another one. So this reaction is used to obtain iron from iron ore. So iron ore is the stuff you dig up in the dirt, and then you have to do a chemical process to get the iron out of it. So this iron ore has iron oxide in it, iron 3 oxide, Fe2O3, and they react it with carbon monoxide, and it produces iron and carbon dioxide. So this is telling us the reaction of 185 grams of iron 3 oxide with 95.3 grams of carbon monoxide produces 87.4 grams of iron. Find the limiting reactant, the theoretical yield, and the percent yield. So we read the question, we go back and we put the numbers under their formulas. So 185 grams of this, 95.3 grams of that, and it says 87.4 grams of iron. And now, what seems odd about this? They gave us a massive product. Well, usually they make us calculate that, right? Well, let's look at what we're asked to find. Limiting reactant, okay. Theoretical yield and percent yield. Percent yield is the actual yield divided by the theoretical yield. Times 100. The theoretical yield is what we've been calculating But how are we going to know what the actual yield is? They have to tell us. So what they're doing here is they're saying the reaction of this and this produces this. This is the actual yield. They have to tell that to you in a problem. So theoretical yield and percent yield. If we want the percent yield, we need to find the mass of this same product. There's two products here. There's iron and there's carbon dioxide. Carbon dioxide is everywhere. That's not a useful product. What we're interested in here is the iron. We need to calculate the mass of this. So I wrote this under here, but now we realize, well, that was the actual yield. So let's just erase that. And what I'm trying to find is the theoretical yield, grams of iron, if everything went perfectly. This is saying how much was actually made. So we're going to do those same two calculations, grams to moles to moles to grams. So 185 grams of iron to moles of iron. No, stop me when I do that. I had my iPad zoomed in and I just saw Fe. This is Fe2O3. 2 moles of Fe2O3. 2 moles of what I'm trying to find. Moles of iron. And then 2 grams of iron. So it's moles of this, grams of this to moles of this, to moles of that to grams of that. Bless you. So again, we're just going to put the units in so they cancel out. Moles in the middle. Look at the balanced chemical equation. 1 mole of Fe2O3 gives 2 moles of iron. I like this last one because that's just an element. So 55.85 grams is 1 mole. And then I'm going to have to calculate this. So 2 times the mass of iron plus 3 times the mass of oxygen. Two times 55.85 plus 3 times 16, 159.7 grams per mole for the iron oxide. So 1 mole weighs 159.7 grams. Everybody okay? 185 divided by 159.7 times 2 times 55.85. So 129.39 grams of iron, and that would have 3 significant figures. Do not round the number yet, because we're going to have to use the theoretical yield in a calculation to get the percent yield. Okay, so one calculation down. Now we need to take the grams of carbon monoxide and figure out how much iron if all of that was used up. If you just had to take a guess, what do you think is going to be the limiting reactant in this problem? What should be the limiting reactant? The iron oxide. Because that's what you're digging up, what you're mining, and carbon monoxide is what you're using to get the iron out of it. There should be an excess of this. That would be our guess. but we don't want to just go on guessing, so we're going to do the stupid calculation. Sorry, did I say that out loud? So grams of carbon monoxide to moles of carbon monoxide to grams of iron, sorry, to moles of iron to grams of iron. Once you get the hang of dimensional analysis, these questions are not difficult, they're just a bit tedious. Okay, so again, I like moles in the middle first. 2 iron, 3 CO. So 2 moles of iron for every 3 moles of CO. The last term is the same because it's the molar mass of iron, which has not changed in the last 5 minutes. Molar mass of carbon monoxide. Now that's the mass of oxygen, carbon, 12.01, plus the mass of oxygen, which is 16. So 28.01 grams. That is the sound of students going from the solid state directly into the gas state and leaving the building. Feel free to shut the door if it bothers you. 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals